So I could continue on talking about industrial AI and robotics for the entire episode, the entire interview. I've written a bit about industrial AI and I find it a fascinating topic. But I also want to touch on some of the research interests that you mentioned earlier. In particular, you talked about this junction of unsupervised and reinforcement learning and some of the work you're doing there. Unsupervised learning is something that has been a goal from a research perspective for a while for its data efficiency, but it's really played out in big ways in natural language processing recently.
Mhm.
Um, Talk a little bit about that junction and where you see it being interesting.
Yeah. So, as you know, Sam, I've been working on reinforcement learning for a very long time, right? And
Yep.
reinforcement learning is, well, it's trial and error learning, and it's something we're very familiar with as humans. When we see a child learn to crawl, learn to run, that's reinforcement learning. And when we train a dog to, maybe sit, that's reinforcement learning. We say sit and it sits, we give it a treat, and if it doesn't sit, we might yell at it, and from that feedback, it figures out what it means to sit and acquires that skill, right? Listening and executing. And so that's reinforcement learning. And a lot of the big successes in reinforcement learning that we've seen so far have been in simulation, right? So, arguably, the most famous success, AlphaGo, right? The best computer Go player and beating the best human players out of DeepMind. Reinforcement learning played a very big role in that because it was playing against itself over and over and over to become better. But it's all in simulation. Same with many video games, a lot of simulated robotics results. Um, but the question is, when you try to transition from simulation to real world, there are a few things you can do. Of course, you can say, "Hey, maybe that my simulator can be perfectly matched with the real world, and that can help you." But ultimately, you want to be more data efficient. Um, you want to not just learn from reward. You want to learn in other ways. You want to not just do something for a minute and at the end know whether you were right or wrong. No, you want to have feedback. That's much denser, much more informative. And naturally, reinforcement learning doesn't really do that in its kind of vanilla form. But we've seen, as you said, in natural language processing, we've seen unsupervised learning, which is learning from just vast amounts of text. And so, to make the analogy there, maybe in natural language processing, you want to classify the sentiment. Is this a positive or a negative review? Or is this a, I don't know, a correct English sentence or a broken English sentence? Things like that. You want to learn to classify that, and instead of just generating examples of positive and negative uh, articles, you would instead first, because that would take a lot of annotated training, that you'd first train on just predicting the next word in a sentence on all the text you can find on the internet. Once you're really good at that, you must have internalized something inside the neural network about language and its meaning, such that now from a few examples you understand positive or negative sentiment classification. And so the question is, can we do the same thing in reinforcement learning? Can we have this auxiliary, unsupervised task that has a lot of signal that's not directly the reinforcement learning signal, but still signal to learn from for the neural network to then quickly acquire a new skill? And so we've been working on that quite a bit in the last year and a half. And so what we've seen, and it's not just us, also some people at NYU, Montreal, and so forth, um, we've actually been able to bridge the gap between what happens when you learn. Let's say a robot has to learn some skill, let's say running or maybe crawling and so forth. When the robot has to learn it with having full access to its entire configuration at all times, all its joint angles, its position, its orientation, that's full access, full state access. That always learned pretty fast, but it would learn slow if all it gets to see is a video stream of itself, because that's maybe 100 by 100 image, so 10,000 pixels. It's much higher dimensional than the succinct state description of the robot. And so what we saw is that massive gap, the learning efficiency when learning from access to state, which was quite efficient, compared to learning with access to image input only, was just this massive gap.
Hmm.
And so the question is, how do we bridge this? And we did it with unsupervised learning effectively. So as the robot is doing its trial and error, instead of only paying attention to rewards and trying to become better based on was this a good or a bad run so far, it is also doing unsupervised learning on the images it's seeing. And what it means specifically in our case is we did something called contrastive learning. So in contrastive learning, what you do is you want to learn what's in an image. But how do you learn it if nobody tells you what's in an image? Well, here's the idea. Imagine you just download two images and you don't know what's in them. You have no idea what's in them. But now, for one of the images, you make a duplicate, but a modification as you duplicate it. So maybe you have an image and you crop it in two different ways. So now I have two different crops of the same image. And then there's the other one. Now, the two different crops of the same image, even though you don't know what's in it, you know they have the same thing in it. And it's different from what's in the other image. Most likely, if you randomly download two images, most likely the other image has something else.
Hmm.
And that's really where the signal comes from. Now, you train your neural network to understand that these two crops of that same first image, neural network should know that's the same. Doesn't know what it is, but it should embed it somewhere in a space where it puts those two close together, and the other image should be put far away from it. That idea turns out really, really powerful. It's been shown to work really well by Jeff Hinton and collaborators, as well as Kam Ming Hui and collaborators, on doing that on images, followed by image recognition training, and it's very, very efficient. We can do the same thing in reinforcement learning from images. So you apply the same idea. What the robot is seeing now versus what it's seeing at a different time. Well, thing is seeing now, you take two different crops, and that is still the same thing. And the neural network learns that there's two views of the same thing and different from the other thing. Very simple idea conceptually, but very, very powerful. You train that way, all of a sudden, you can train almost as efficiently from image inputs as with direct access to state. This one, we evaluated this on the kind of standard DeepMind control suite simulated robotics environments.
Hmm. Um, in the there's a whole area of research around multitask learning that seems to suggest, although there's certainly arguments against this, that networks generalize better when they have more to do. Essentially,
Hmm.
I'm wondering if part of what you're seeing is the effect of just giving the network something else to learn, as opposed to the unsupervised um, task contributing to kind of the core reinforcement learning thing that it's supposed to learn.
So you're absolutely right in that multitask tends to help. I mean, it's why when for example, at Covariant, we train the same neural network across many application domains because it'll help to train across all those domains, use the same network rather than specialize to each one of them. Same in the research here, when we train a neural network for multiple tasks, often it can do better. But the beauty about bringing in the unsupervised loss is that you can think of the unsupervised loss as multitask, where
Mhm.
the multitask additional thing doesn't require you to do any annotation, doesn't require you to give any reward signals. So it's like the
Got it.
cheapest way to achieve multitask
Mhm.
in terms of human effort. Cheapest way. Still a lot of compute required. Just to be clear, still
Yeah,
a
yeah.
lot of compute involved.
Yeah, I think the analogy that I was coming from is like in NLP, when you're training BERT or something, and you have this unsupervised formulation of the problem.
Hmm.
The problem that you're trying to solve in a lot of ways is directly related to you're in building the language model, blanking out the words is like that's, teaching you language. And I'm wondering if there's a distinction between the second task, is the second task, it just happens to be an unsupervised task,
Hmm.
and the relationship between that and the core reinforcement learning task that you're trying to solve. I'm not sure that I'm completely articulating the question in a clear way, but the idea is the unsupervised tasks kind of core to, does it inform the core reinforcement learning process and that loss, or is it just an ancillary other thing, and it's the multitask aspect or the other task that is what creates value or causes you to increase performance?
Right. So you're actually getting at something that we're working on right now. So let me say a bit more about that. So to very directly answer your question, I think when we use the contrastive loss on a given image compared to an image at a different time, um, we're not tying it very directly to the locomotion task versus crawling versus maybe sit or maybe push an object. It's not very closely tied to that. I'm inclined to think of it as it's like learning the vision system of the robot. It's learning to see and understand, that it's seeing the same thing in these two situations versus seeing something else there. But it's not learning about how the world works. And that's kind of what you're getting at. In
Hmm.
reinforcement learning, you try to achieve goals. Your robot's supposed to get from point A to point B, or achieve something with the objects in front of it, or it could be in a game. You're supposed to get a high score in the game
Yeah.
and so forth. And so this whole notion of achieving goals and how the world works, I think is a natural complementary aspect. So imagine you, in the unsupervised sense, you've been able to complement your reinforcement learning to get a bit of a vision system trained.
Hmm.
But now what you also want is effectively a how does the world work system, such that when I'm asked to do something in this world as a robot, I already kind of know how the world works. I don't have to flail my arms a gazillion different ways, and I don't have to learn that if I don't touch an object, it's not going to move, kind of thing.
Yeah.
I know that the world works with contact forces and so forth. So if I want block A and block B, well, block B that's on the bottom has to be on the table first, and then those things are things that don't come from what I just described, the contrastive learning I just described. You need a temporal aspect to it.
Hmm.
And so that I think is one of the important next steps. It requires more compute, and that's probably why it's coming a bit later in the progression of research overall. But the notion there would be, can you understand what are natural video sequences? So if you download a lot of video, what does it tend to look like? And that's a very hard problem because video is very high dimensional, meaning that training your neural networks for video prediction or understanding which videos are more related or less related to each other is computationally an intense problem. It's also the kind of problem that, I'm sure you're well aware, Jan LeCun's been talking about for a very long time when he gives the cake analogy of reinforcement learning as the cherry on the cake, is the reward signal, but the unsupervised is the most of the cake, right? And the icing is the supervised learning. Unsupervised is most of it. What he thinks of is video. In the context of robotics, at least, they think of video. Robots have watched so many videos that they know how the world works. A lot of research still has to be done there, but I think that'll be really important.
Hmm.
And then there's the third part. So there's the understanding what you're looking at. It's part one. We made a lot of progress on that. Then video understanding, behavior understanding in that sense, how the world works. The third part is for the robot to have its own skills. And that's where it gets much closer to what you're talking about and something we're actively working on, which is, can you let a robot just spend time on its own? Just the robot's just on its own in a room or wherever it is. And can you make it spend its time meaningfully? Effectively play. What for children we would call play. You say, oh, kid is just playing. But actually, yeah, kid is just playing. You might say, well, it'd be nice if it did some chores or whatever. But actually, the kid is just playing. It's actually learning about the world. It's the kid now understands, especially young kids, they understand how now objects interact. They understand how the world works from interacting with it. And that kind of play is another important component. If we think about the long-term future of robotics, if we want to get to less supervision, less needing to train everything into the robots, just let them try things on their own.
Why
The
would
big
that kind of play be different from the goal-directed exploration that we do today in RL?
so there is a good amount of work that's already happening in RL on essentially getting this kind of play to surface. So goal-directed exploration is a great example. There is other work that kind of similar, but it's called then curiosity or something like that, where
Novelty or yeah.
yeah, essentially you give rewards for experiencing something that you haven't experienced before.
Mhm.
And I think that's worked really, really well in environments that are, I would say, somewhat closed. Meaning, if you think about, let's say, an Atari game, which is a popular reinforcement learning benchmark environment, usually there's a right way to play the game, and there's not too many other things you can do, or you die. And that's what I mean with a kind of closed environment. And if you're curious and you try to experience new things, well, you've died many times in the game. That's not new anymore. So the new things are the things that take you to the next level in the game. And so there's a very natural alignment between novelty and the actual task that we care about. And that's why curiosity, goal-oriented exploration, and so forth have had a great amount of success. Um, but that breaks down in the real world where there are so many things you could do. Or even in some games like Minecraft, which is becoming a new benchmark that people get excited about for this exact reason. In Minecraft, you can build so many different things. And so just experiencing something novel, you can keep doing that forever and
Mhm.
never learn something interesting. And I think that's kind of the next step there. And that's maybe where I think of things like children's play as being a bit different, because it seems like somehow they have a bit more intuition than our current AI systems about what's interesting play, as opposed to just what's novel but actually not that interesting.
Interesting, interesting.